in the MSc Chemistry Curriculum, Semester I, at Fakir Mohan University, Vyasa Vihar, Balasore. Paper CH412 is Inorganic Chemistry I. Unit 1 of CH412 is titled Symmetry and Group Theory in Chemistry. This unit forms the theoretical foundation for understanding molecular geometry, optical activity, bonding, and vibrational spectroscopy. 1. Symmetry elements and operations. A symmetry operation is a movement of a molecule such that its post-operation orientation is indistinguishable from its original orientation. A symmetry element is a point, line, or plane with respect to which the symmetry operation is performed. Symmetry element. Symbol. Operation. Example. Identity. E. Doing nothing, 360 carat, circ rotation. All molecules. Proper axis of rotation. C_n. Rotation by an angle, theta equals, frac 360 carat, circ n. C_2 in, text h_2, text O, C_3 in, text nh_3. Plane of symmetry, sigma. Reflection across a plane, sigma_v, sigma_h, sigma_d, sigma_v in, text h_2, text O, sigma_h in, text c_6, text h_6. Center of inversion, I. Inversion through a central point, x, y, z, right arrow, x, y, z, text sf_6, trans, text ptcl_2, text nh_3_2. Improper axis of rotation, s_n. Rotation by, frac 360 carat, circ n, followed by reflection, sigma, perpendicular to the rotation axis. S_4 in, text ch_4. Types of planes, sigma, sigma_h, horizontal, perpendicular to the principal axis of highest order. Sigma_versus, vertical, contains the principal axis. Sigma_d, dihedral, contains the principal axis and bisects the angle between two C_2 axes perpendicular to the principal axis. 2. Fundamental group theory rules. A mathematical group G is a set of elements together with an operation that satisfies 4 essential criteria. Closure. If A in G and B in G, then A, CDOT B equals C in G associativity, A, CDOT B, CDOT C equals A, CDOT B, CDOT C. Identity element. There exists an element E in G such that A, CDOT E equals E, CDOT A equals A inverse element. For every element A in G, there exists an inverse A_(-1) in G such that A, CDOT A_(-1) equals A_(-1). CDOT A equals E. Key concepts and definitions. Order of a group, H, the total number of symmetry operations in a point group. Subgroup, a subset of operations within a group that itself satisfies all group requirements. Lagrange's theorem, the order of a subgroup, K, must be an integer divisor of the order of the main group, H. Conjugacy class, a set of elements, A, B, linked by a similarity transformation x_(-1). AX equals B, where X is any element of the group. 3. Point symmetry groups and classification. Molecules are categorized into point groups based on the complete set of symmetry operations they possess. Non-axial groups, C_1, no symmetry except E, C_s, only E and sigma, C_I, only E and I. Low symmetry axial groups, C_n, C_nv, text H, 2, text O, right arrow C, 2v, text NH, 3, right arrow C, 3v, C_nh. Dihedral groups, D_n, D_nh, text BF, 3, right arrow D, 3h, text PTCl, 4 carat 2, right arrow D, 4h, D_nd, text allene, right arrow D_2d, staggered ethane, right arrow D_3d. High symmetry, polyhedral groups, T_d, tetrahedral, e.g., text CH, 4, O_h, octahedral, e.g., text SF, 6, I_h, icosahedral, e.g., text C*60. Linear groups, C*infinity V, heteronuclear linear, e.g., text HCl, D_h, homonuclear linear, e.g., text O_2, text CO_2. 4. Matrix representations of symmetry operations. Each symmetry operation can be represented mathematically as a transformation matrix acting on coordinate vectors x, y, z, identity, E. Inversion I. Rotation C_n along z-axis. The character G of an operations matrix representation is the sum of its diagonal elements, the trace of the matrix. 5. Great orthogonality theorem, GOT, and representation theory. A set of matrices representing the symmetry operations of a point group forms a representation, gamma. Reducible representation, gamma underscore text, red, a high-dimensional matrix representation that can be simplified into lower-dimensional block matrices. Irreducible representation, gamma underscore text, R, a fundamental representation that cannot be reduced any further. Statement of the great orthogonality theorem, GOT, where H equals order of the point group. L underscore I, L underscore J equals dimensions of the ITH and JTH irreducible representations. D underscore I, R, asterisk, Mn, equals element in the MTH row and NTH column of matrix for operation R, delta equals Kronecker delta, delta H equals 1 if I equals J, else O. 5 key rules derived from GOT. The sum of the squares of the dimensions, L underscore I, of all irreducible representations equals the group order, H, sum underscore I L underscore I squared equals H. The sum of the squares of characters in any irreducible representation equals H, sum underscore R, word, G underscore I, R, word, squared equals H. The characters of two different irreducible representations are orthogonal, sum underscore R, G underscore I, R, CDOT, G underscore J, R, equals 0 for I, neg J. The number of irreducible representations in a point group equals the number of conjugacy classes. In a given class, the characters of all operations are equal. Standard reduction formula. To find how many times an irreducible representation, gamma underscore I appears inside a reducible representation, gamma underscore text red, use, where G underscore R is the number of operations in class R, G underscore text red is the character of the reducible representation, and G underscore I is the character of the ITH irreducible representation. Table condenses all symmetry information of a point group into 4 main quadrants, C underscore 2V, E, C underscore 2, sigma underscore V, XZ, sigma underscore V, Yas, linear functions, quadratic functions, A underscore 1, 1, 1, 1, 1, ZX squared, Y squared, Z squared, A underscore 2, 1, 1, minus 1, minus 1, R underscore ZXY, B underscore 1, 1, minus 1, 1, minus 1, X, R underscore Y XZ, B underscore 2, 1, minus 1, minus 1, 1, Y, R underscore XYs. Mulliken symbols nomenclature. A, 1D representation, symmetric with respect to principal axis C underscore N, G, C underscore N equals plus 1. B, 1D representation, antisymmetric with respect to principal axis C underscore N, G, C underscore N equals minus 1. E, 2D degenerate representation. T or F, 3D degenerate representation. Subscripts 1/2, symmetric plus 1, antisymmetric minus 1 to a perpendicular C underscore 2R, sigma underscore V. Symmetric G, Girardet, antisymmetric U, Ungaret. With respect to inversion I, primes, symmetric, antisymmetric to a horizontal plane, sigma underscore H. Practical applications in chemistry. Optical activity, chirality. A molecule is optically active, chiral, if it lacks an S underscore N axis, which also excludes sigma and I, as S underscore 1 equals sigma and S underscore 2 equals I. Dipole moment. A molecule has a permanent dipole moment only if it belongs to C underscore 1, C underscore S, C underscore N, or C underscore NV point groups. Spectroscopy, IR and Raman activity. A vibrational mode is IR active if its transformation matches linear coordinates x, y, z. A vibrational mode is Raman active if its transformation matches binary product quadratic coordinates x squared, y squared, z squared, xy, xz, yes. Where would you like to apply these concepts next? Practice determining point groups of common molecules. Solve an example using the reduction formula. Explain how to construct a character table using GOT.